Today we're going to be looking at something pretty cool.
Oh, yeah.
Multiple principal element alloys.
MPEs,
yeah. And we're going to be talking about a research article that really gets into the nitty-gritty of these alloys.
A fascinating area.
Yeah, so these aren't your typical,
No.
steel or aluminum.
Right, exactly.
We're talking about metals that are made up of at least five elements.
At least 5.
In near equal proportions.
Yeah, and that's what really makes them stand out.
Yeah, and why it matters is because these alloys, these MPEs, have the potential to kind of revolutionize a bunch of different industries by having these really unique properties that we can sort of fine-tune.
Yeah, and that's the exciting part, is the tunability of these properties.
Right, so what makes them so special? I mean, what is it about having all these elements all mixed together that makes them so different?
Well, it's funny because sometimes you'll see it referred to as high entropy alloys. Yeah. And that kind of gets to the heart of it. If you think about a traditional alloy, you might have, 1 or 2 principal elements and then a few little additions to kind of tweak the properties. Mm-hmm. But here, because you have this near equal proportion of 5 or more elements, you get a much higher degree of disorder in the atomic structure.
Like organized chaos.
In a way.
Yeah.
And that disorder, that entropy, actually contributes to some really interesting properties.
So it's not just a random mixing. There's actually science behind choosing those elements.
Oh, absolutely. Scientists are using some really sophisticated tools and concepts to predict how these elements will interact with each other.
Can you give us a little peek behind the curtain there? What kind of concepts are we talking about?
Well, one of the key concepts is this idea of mixing entropy, which we kind of touched on already. It's basically a measure of how disordered a system is.
Right.
The more elements you add, and the closer their proportions are to each other, the higher that mixing entropy will be.
Okay, so like a high mixing entropy basically means things are all jumbled up.
Pretty much, yeah. And that jumbling up actually can lead to increased stability in some cases.
Interesting. So it's like the more chaotic it is at the atomic level, the stronger it becomes?
In some ways, yes. But there's another factor that's really important too, and that's mixing enthalpy.
Okay, enthalpy. So what's that all about?
Mixing enthalpy is a little bit trickier to explain, but essentially it relates to the energy involved in mixing the elements together.
Okay.
So some element combinations, they're like oil and water. They just don't want to mix.
Yeah, they're not going to get along.
Exactly. And that can lead to phase separation or the formation of unwanted compounds.
Oh, I see. So it's not just about randomness, but also how much the elements actually like being around each other.
Right. And then on top of that, you have other factors like valence electron concentration, which is basically the average number of electrons that each atom contributes to the alloy.
So like their bonding power?
You could think of it that way, yeah. And then there are parameters called the omega factor and the delta factor.
Omega and delta. That sounds pretty intense.
They're essentially mathematical expressions that take into account all those things we've talked about. Yeah. Entropy, enthalpy, valence, electron concentration. They help scientists predict whether or not an alloy is likely to form a single, stable, solid solution.
Which is often the goal, right?
Yeah, a single-phase solid solution often leads to desirable properties like high strength and good ductility.
Okay, so scientists use these parameters to kind of predict whether the alloy is going to be a hit or a miss.
Exactly. And they can tweak the composition based on those predictions to try to get the desired outcome.
Fascinating. So in this particular research that we're diving into today, what kind of alloys were they cooking up?
They were focusing on a really interesting family of alloys based on cobalt and chromium.
CoCr, okay.
Yeah. And they were specifically looking at a system called CoCr 100-BZRX.
That's a mouthful.
Yeah, it's a little bit of a tongue twister.
Yeah.
But essentially what it means is that they were varying the amounts of cobalt and chromium and then adding in varying amounts of titanium, niobium, and zirconium.
Okay, so it's like a recipe where you're adjusting the ingredients to see what kind of cake you get.
Exactly. And they were systematically changing the value of X in that formula to see how the composition affected the final microstructure and properties.
Clever. So it's not just theory. They actually made these alloys in the lab.
They did. They used a technique called vacuum arc furnace melting.
Wow, that sounds pretty high tech.
Yeah, it involves melting the metals together in a vacuum chamber using an electric arc.
So basically, they're zapping these metals together to create these new alloys.
Yeah, and then they used a process called suction casting to create solid rods of the alloys.
Suction casting. Now, that's a new one for me.
Yeah, so suction casting involves rapidly cooling molten metal in a mold. And it's a really important step because it helps to control the microstructure of the alloy.
The microstructure. That sounds like something you'd need a microscope to see.
You got it. The microstructure is the arrangement of grains and phases within the material.
Oh, okay. So by controlling how fast the metal cools, they can actually influence how those tiny grains arrange themselves.
Exactly. And that has a big impact on the properties of the alloy.
So it's not just what you put in, it's also how you cool it down.
Absolutely. It's all interconnected. And to analyze these microstructures, they use some really powerful tools like scanning electron microscopy, or SEM.
SEM, okay. And what does that tell them?
SEM allows you to see the surface of a material at very high magnifications. So they can see the individual grains and phases and how they're arranged.
So like zooming in on a map, but for metals.
That's a good analogy.
Pretty cool. Did they use anything else to analyze these alloys?
Yeah, they also used energy dispersive X-ray spectroscopy, or EDS.
Okay, so we've got SEM and EDS. What's EDS all about?
EDS is a technique that's often used in conjunction with SEM, and it allows you to determine the elemental composition of the material.
So they can see exactly what's in those tiny grains.
Yep. It tells them how much of each element is present in different areas of the alloy.
So they're like metal detectives figuring out the secrets of these alloys.
That's a fun way to think about it.
Mm-hmm.
And finally, they used X-ray diffraction, or XRD, to get even more information about the crystal structure of the alloys.
XRD. Okay. And what does that tell them?
XRD helps determine the arrangement of atoms within the material, providing information about the different phases that are present.
So like a blueprint for the atoms.
In a sense, yes. It gives them a detailed picture of the crystal structure.
Wow, that's impressive. So they've got these powerful tools to analyze these alloys, but what did they actually find? Did those predictions based on mixing entropy and all that stuff actually hold up in the real world?
Well, that's where things start to get really interesting, because there were definitely some surprises when they compared the theoretical predictions to the actual experimental results.
Ooh, surprises. Tell me more.
Well, the models predicted that many of these alloys would form these nice single-phase solid solutions, a perfect blend of all those elements.
A perfectly mixed smoothie.
Yeah, something like that. But when they actually looked at the alloys using SM, EDS, and XRD, they found that things weren't always so simple.
So the smoothie curdled.
You could say that. Yeah. In many cases, they observed multiple phases in the alloys, including some intermetallic phases.
Intermetallic phases, what are those?
Intermetallic phases are compounds that form between two or more metals. They have specific crystal structures and compositions.
Oh, okay. So it's like those elements decided they liked each other a little too much and formed their own little club within the alloy.
You could think of it that way, yeah.
And that wasn't what they were expecting?
Not necessarily, no. Some of those intermetallic phases can actually be beneficial. They can increase the strength of the alloy, for example.
So not all surprises are bad.
Exactly. But in some cases, the formation of these intermetallic phases can also lead to undesirable properties, like brittleness.
So it's a bit of a mixed bag then. They got some surprises, some good, some maybe not so good. This is reminding me of that whole mixing enthalpy thing you mentioned earlier.
Yeah, and that's one of the key takeaways from this research. It highlights how complex these MPE alloys really are.
Even with all those fancy models and predictions, there are still things that can surprise you.
Absolutely. It's a reminder that we still have a lot to learn about how these multi-element systems behave.
So real-world behavior threw a bit of a wrench into their plans.
In a way, yes. But that's what makes this research so valuable. It's pushing the boundaries of our understanding.
Okay, so we've got these CoCr-based alloys. They've got some surprises in their microstructure, and we're starting to see that those surprises aren't necessarily bad. But what about the mechanical properties? I mean, that's what we really care about at the end of the day, right? How strong are these things?
That's a great point. We've talked a lot about the theory and the analysis, but the next step is to see how these alloys actually perform.
All right, let's get down to business. We'll tackle those mechanical tests in part 2. Okay, so we're back. And we're ready to dig into these mechanical tests. We left off talking about how those CoCr-based alloys had some unexpected phases pop up.
Right. Some surprises in the microstructure.
Exactly. But surprises aren't always bad, right? So let's see how the surprises played out when they actually put these alloys to the test.
All right, so they started with hardness tests, which is a pretty standard way to measure how resistant a material is to scratching or denting.
Makes sense. The harder it is, the tougher it is, right?
Generally, yeah. And what they found was that adding more cobalt and chromium significantly increased the hardness of the alloys.
Okay, no big surprise there. Cobalt and chromium, those are pretty hard metals on their own.
Right, but here's where it gets interesting. They noticed that the presence of those intermetallic phases, those ones that weren't predicted by the models.
The surprise guests at the microstructure party?
Yeah, exactly. Those phases actually seem to boost the hardness even further.
Wait, so those unexpected phases actually made the alloys stronger?
In this case, yes. It's a good reminder that sometimes those deviations from the ideal can actually lead to some beneficial properties.
So it's like a little bit of chaos can be a good thing.
Sometimes, yeah. Of course, it's not always that simple.
Right, there's got to be a trade-off somewhere. What was the downside?
Well, the compression test revealed that some of the alloys, especially the ones with higher amounts of those intermetallic phases, tended to be a bit brittle.
Brittle, so they could crack or break more easily.
Right, they fractured before they had a chance to undergo much plastic deformation.
Okay, so they were hard, but not very flexible. That's not ideal if you need a material that can bend or withstand impacts.
Exactly. Ductility, that ability to deform without breaking, is often a very desirable property.
Definitely. So it's a balancing act. You want the hardness, but you don't want it to be so brittle that it just shatters.
Right. And it's not just those intermetallic phases that affect the mechanical properties.
Yeah.
They also found that the BCC1 phase, remember that body-centered cubic structure we talked about earlier?
Yeah, I remember. It was one of the phases they found in those alloys.
Right. Well, the BCC1 phase seemed to play a big role in determining the yield strength of the alloys.
Yield strength. Remind me what that is again.
Yield strength is basically the amount of stress that a material can withstand before it starts to permanently deform.
Okay, so like how much force you can put on it before it bends out of shape.
Exactly. And they found that the alloys with more of that BCC1 phase generally had higher yield strength.
So the more BCC1, the stronger the alloy.
In general, yes.
Interesting. So we're seeing that these microstructures are really complex, and the properties of the alloys depend on this delicate balance of all these different factors.
That's exactly right. And it highlights why this research is so valuable. It's helping us to understand all these nuances and how they affect the final product.
Right. It's not just about saying MPE alloys are strong or MPE alloys are brittle. It's about understanding how all these pieces fit together.
Exactly. It's about understanding the interplay of the composition, the processing, and the resulting microstructure.
So ultimately, we want to be able to engineer these alloys for specific purposes, right? We need to know which knobs to turn to get the exact properties we want.
Absolutely. And this research is giving us valuable insights into how we might be able to do that.
So it's not just about strength, it's about a whole suite of properties, right? You mentioned things like corrosion resistance and high temperature stability earlier. How do those factors come into play with these MPE alloys?
Well, those are definitely important considerations, especially when you start thinking about real-world applications.
Right, because it's one thing to make an alloy that's strong in the lab, but if it falls apart in a harsh environment, it's not very useful.
Exactly. And that's where things like corrosion resistance and high temperature stability become really important.
Okay, so let's talk about corrosion first. How do these MPE alloys stack up against traditional alloys in that department?
Well, one of the interesting things about MPE alloys is that they often have a very high resistance to corrosion.
Is that because of those multiple elements they have?
Partly, yes. Some of those elements, like chromium, for example, are known for their corrosion-resistant properties. And when you combine them in an MPE alloy, you can get some pretty impressive results.
So we're talking about alloys that can basically laugh in the face of rust.
It's definitely a possibility.
That's pretty awesome. Okay, so what about high temperature stability? Can these MPE alloys take the heat?
That's another area where they have a lot of potential. Traditional alloys often start to weaken or even melt at high temperatures, but MPE alloys, with their high entropy and complex microstructures, can sometimes handle those conditions much better.
So we're talking about alloys that can withstand the heat of a volcano.
Maybe not a volcano, but they definitely have potential for high temperature applications.
Wow, it sounds like these alloys have a lot to offer. But I know we've just scratched the surface here.
Oh, absolutely. We focus mainly on mechanical properties and a bit on corrosion and high temperature stability, but there's so much more to explore.
Like what? Give me a teaser.
Well, some MPE alloys have shown really interesting magnetic properties, for example.
Really? So they could be used for things like data storage or sensors.
Exactly. And others have potential in electronics, like semiconductors or thermoelectric devices.
It sounds like we're just at the beginning of this whole MPE alloy journey. There's so much more to discover.
Absolutely. And this research that we've been discussing, it's really paving the way for some incredible advancements.
This is definitely one of those stay tuned for more moments. But before we get too carried away with all the amazing possibilities, let's take a step back and talk about what this all means for the future of these materials. What are the next steps? What are the challenges?
That's a great point. We've laid the groundwork, we've explored the complexities, and we've seen the potential. But now it's time to look ahead.
All right, let's do it. We'll wrap things up and explore those exciting possibilities in part 3.
Okay, so we're back for the final part of our deep dive into these incredible MPE alloys. We've talked about their designs, the surprises they've thrown at us, and those amazing properties they have.
It's been quite a journey.
Yeah, it has. So where do we go from here? What's next for these materials?
Well, the researchers in this paper, they hinted at some really exciting stuff.
Ooh, like what? Well, they suggest that we might be able to unlock even more potential if we could get even more control over the cooling rate.
Ah, the cooling rate. We talked about how even with suction casting, things can get a little, well...
a little wild.
Yeah, those intermetallic phases still manage to sneak in.
Right, exactly.
Yeah.
So what if we could push those cooling rates even further?
Like how much further are we talking about?
Well, imagine cooling those alloys down so fast that the atoms basically freeze in place.
Like hitting a pause button on a super speed movie.
Exactly. Before they even have a chance to rearrange themselves and form those different phases.
So we're talking about some seriously rapid cooling here.
Oh yeah, we're talking about cutting-edge techniques like melt spinning.
Melt spinning. Okay, what's that?
So basically you take the molten metal and you propel it onto a spinning copper wheel that's rotating super fast.
Whoa!
And that causes the metal to cool down incredibly rapidly.
I can imagine. Is there anything else besides melt spinning?
Yeah, there's another technique called laser surface melting, where you use a high-powered laser.
Lasers.
Yep, lasers. You use them to melt and then re-solidify a very thin layer of material incredibly quickly.
So we're talking like fractions of a second here.
Even faster in some cases.
Wow, that's amazing. But what's the big deal with all this super fast cooling? Why go to all that trouble?
Well, the idea is that if we can cool things down fast enough, we might actually be able to achieve those single-phase solid solutions.
Ah, the ones that the theoretical models predicted.
Exactly. The ones that are supposed to have those really exceptional properties.
So we could potentially make those alloys even stronger and more ductile.
That's the hope. And who knows, we might even uncover entirely new properties that we haven't even thought of yet.
Now that's exciting. Are we talking about alloys that are stronger than steel, more flexible than rubber, and can handle the heat of a furnace all at the same time?
Well, maybe not all at the same time, but the possibilities are certainly vast.
Okay, let's rein it in a little bit before we get too carried away. We've talked about those incredible cooling techniques, but we also talked about mixing enthalpy earlier.
Right, that idea that some elements just really like to pair up with each other.
Yeah, and that can lead to those intermetallic phases forming, even if we try to cool things down super fast.
Exactly. So it's not just about the processing, it's also about the elements themselves.
So what can we do about that?
Well, researchers are starting to think about how they can strategically select elements that are more compatible with each other.
Like a matchmaking service for metals.
Yeah, something like that.
Yeah.
By choosing elements that are more likely to play nice together.
We can minimize the formation of those unwanted phases.
Precisely. So it's a combination of clever element selection and those advanced processing techniques.
Wow, it's like a whole new level of alloy design. We're not just mixing metals anymore, we're orchestrating them.
That's a great way to put it.
Okay, so imagine being able to design an alloy with the exact combination of strength, flexibility, corrosion resistance, and whatever other properties you need.
It's mind-blowing.
It really is. So where could these alloys take us? What kind of amazing applications are we talking about?
Well, let's start with aerospace. Imagine lightweight, ultra-strong MPE alloys that can handle the extreme temperatures and stresses of hypersonic flight.
So we're talking about planes that can travel faster than the speed of sound.
Maybe even spacecraft that can venture further into space than ever before.
That's incredible. What else?
Well, in the energy sector, think about power plants that can operate at much higher temperatures.
Some more efficient energy production.
Exactly. And it could also revolutionize renewable energy technologies like solar thermal power.
Wow. So we're talking about harnessing the power of the sun with these alloys.
It's a possibility. And then there's the potential for medical applications.
Oh yeah, we talked about that a little bit earlier.
Imagine biocompatible MPE alloys that could be used for things like implants or prosthetics.
Or even those tiny little medical devices that can operate inside the human body.
Exactly. These alloys could really push the boundaries of what's possible in medicine.
It sounds like we're on the verge of a materials science revolution, and these MPE alloys are leading the charge.
I think you're right. But of course, with any new technology, there are always challenges.
Oh yeah, for sure. What kind of challenges are we facing with these MPE alloys?
Well, one of the biggest ones is the cost and complexity of those advanced processing techniques we talked about.
Right, those super fast cooling methods, they're not exactly cheap or easy to scale up.
Exactly. So figuring out how to make those processes more efficient and cost-effective is going to be crucial.
What else? Are there any other challenges?
Well, these alloys are incredibly complex, and we still have a lot to learn about how they behave.
Right, like those unexpected phases that popped up in this research.
Exactly. We need better models and tools to predict those kinds of things and to really optimize the properties of these alloys for specific applications.
So there's still a lot of work to be done.
Definitely. But the progress that's been made in just the past few years is really remarkable.
It's exciting to think about what the future holds for these MPE alloys.
Absolutely. There's so much potential waiting to be unlocked.
Well, this has been an amazing journey into the world of MPE alloys. I've learned so much, and I'm so excited to see where this field goes next.
Me too. It's a fascinating area of research, and I have a feeling we're just getting started.
To everyone listening out there, thanks for joining us on this deep dive. And remember, keep exploring, keep learning, and keep that curiosity alive.